Okay, welcome back. In this lecture, actually deviating from my original plan slightly, I'm going to introduce Fisher projections. We'll use them in the next lecture when we talk about diastereomers and meso compounds. What is a Fisher projection? Well, let's take our trusty molecule here. Let me draw this. So I've got my HCCl iodine's in front, and the Br is in back, like so. Now, there we go, like that. Now what I want to do is I'm going to rotate so that my hydrogen and chlorine are pointing up and down, but they're pointing back into the plane. So rotate. So I'll have my carbon here, and going back behind the plane of the paper is the hydrogen and also the chlorine. And then coming out of the plane is the iodine and the bromine. And this is equal to the following. We'll make a giant plus sign, and then we'll put in the substituents. And this is a Fisher projection. Okay, it's a projection because we're taking a three-dimensional object and projecting it onto 2 dimensions. The important thing to understand is that the horizontal substituents in a Fisher projection are coming out towards you, and the vertical ones are going away from you. Okay? You can do a Fisher projection for compounds with more than one chiral carbon. So, more than one stereocenter. Okay, and so for example, I could, let me take my iodines off here, and I'll just link these guys up. You actually do a version of this in the lab. And now I'm going to go ahead and draw this. Now the thing to remember here, maybe I'll draw it like this. So I've got C, H, C, H, Cl in front, Cl in back, Br in back, sorry, Br in back, Cl in front there. I'm going to rotate it, and I'm going to look at each carbon individually. Okay, so I will draw it like so. I draw a giant double plus here. So I've got a hydrogen up top there, and my carbon here is going back, so it's there. Okay, that's what this line there means. Now I'll turn it. Oh, let me add in the chlorine and the bromine. Now I'll turn it and look at the other one, and I've got chlorine, bromine, and hydrogen. And so you can pretty easily tell just by looking at, the intersections of carbon. I have obviously 4 different things on it. Here I've got 1, 2, 3, and carbon and stuff. That's 4 different things. Notice that this is an eclipsed conformation. If I do this for a whole bunch of carbon atoms, so let's just say I had, 4 carbons. Let's say I had 4 carbons here. Okay, it is tempting to say, all right, here is my staggered conformation. I'll just draw it like this. That would be wrong. Why? Well, look at the top carbon. The horizontal ones are going back. The definition of a Fisher projection, the horizontal ones come out towards you. So what we actually have is our Fisher projection is looking 1 carbon at a time. So if we actually did this Fisher projection. It's like we took this super eclipsed version of this molecule and stretched it out. That's what we would be doing. So it is important to understand what the Fisher projection represents and also why it's useful. Don't always use it, especially in organic chemistry for compounds with just one chiral carbon, but if we have multiple chiral carbons, it can become very useful. All right, so that was the quick little lecture on Fisher projections, and we'll use these a lot more in the next lecture. All right, until next time, stay safe out there. Bye now.